Okay, hello students, welcome to English class today. I hope you are doing fine today. So we are talking about a very interesting topic. It's called Oobleck can't make up its mind, and I think it's really interesting. It's kind of science related. Okay, so we'll get into some scientific terms and things like that. So while we wait for some others to join, I'd like to start with each class with some tongue twisters because there are some good warm-up for like your enunciation, so your pronunciation of words. Okay, so I'll say them once or a few times and then I'll have you guys try them. Okay, so let's start a little simple. So here it is: friendly fleas and fireflies. Say it 3 times fast. Friendly fleas and fireflies. Friendly fleas and fireflies. Friendly fleas and fireflies. Okay, who would like to try this? Jagger, would you like to try? Okay, Nancy, you can go ahead.
Friendly fleas and fireflies.
Very good. Try to say that a little quicker. Quicker.
Friendly fleas and fireflies. Friendly fleas and fireflies. Friendly fleas and fireflies.
So it can be a little tricky there, right? Kyrin, would you like to try?
Friendly fleas and fireflies.
Yeah, great job pronouncing that. Okay, let's try this next one. A proper copper coffee pot. A proper copper coffee pot. Okay, anyone like to try this? Okay, go ahead, Nancy.
A proper copper coffee pot. A proper copper coffee pot.
Very well said. Hi, Lulu. I see you just came in. We are practicing some tongue twisters here. Okay, so a proper copper coffee pot. A proper copper coffee pot. These are very good for practicing your pronunciation. So, would you like to go ahead and try one of these? Lulu?
A proper copper coffee pot.
Very good. Okay, let's try this next one. How can a clam cram in a clean cream can? How can a clam cram in a clean cream can? Okay, so lots of k and gl sounds. Would anyone like to try? Lulu?
How can a clam cram in a clean cream can?
Very well said. Jagger, would you like to try?
How can a clam cream in a clean cream can? How
Okay.
can a clam cream in a clean cream can?
Okay, good try there. So it's clean. Okay, clean. So how can a clam cram in a clean cream can? Okay, go ahead, Nancy.
How can a clam cram in a clean cream can? How can a clam cram in a clean cream can?
Okay, great job. Let's try another one. If a dog chooses shoes, whose shoes does he choose? If a dog chooses shoes, whose shoes does he choose? Okay, lots of ooh sounds. Anyone would like to try? Leilu?
If a dog chooses shoes, whose shoes does he choose?
Thanks, Leilu. Kyron, would you like to try?
If a dog chooses shoes, whose shoes does he choose?
Great job. Nancy?
If a dog chooses shoes, whose shoes does he choose?
Great job. Okay, let's move on. This one's a little easier, but I think it's really funny. So here goes. Fuzzy Wuzzy was a bear. Fuzzy Wuzzy had no hair. Fuzzy Wuzzy wasn't fuzzy, was he? So this was he sounds like Wuzzy. It's really similar. Sounds really similar. Okay. Nancy, you can try this.
Fuzzy Wuzzy was a bear. Fuzzy Wuzzy had no hair. Fuzzy Wuzzy was fuzzy, was he?
Okay, good job. Jagger, I saw your hand was up.
Fuzzy Wuzzy was a bear. Fuzzy Wuzzy had no hair. Fuzzy Wuzzy wasn't fuzzy, was he?
Thanks, Jagger. Very well said. Laylu, go ahead.
Fuzzy Wuzzy was a bear. Fuzzy Wuzzy had no hair. Fuzzy Wuzzy wasn't fuzzy, was he?
Great job. Okay, next one. This one's the last one, and it's a very classical one. You may have heard of this before. So it's Peter Piper picked a peck of pickled peppers. A peck of pickled peppers Peter Piper picked. If Peter Piper picked a peck of pickled peppers, where's a peck of pickled peppers Peter Piper picked? Okay, so a pattern you might notice is that there's a lot of repeated sounds and tongue twisters. Okay, Jagger, would you like to try this really long one? It's a little difficult.
Peter Piper picked a peck of pickled peppers. A peck of pickled peppers Peter Piper picked. Peter Piper picked a peck of pickled peppers. Where's the peck of pickled peppers Piper picked?
Okay, Jagger. Peter Piper. Okay, that's how it's pronounced. Peter Piper picked a peck of pickled peppers. Okay, but good try though. Kaivan, would you like to try?
Peter Piper picked a peck of pickled peppers. A peck of pickled peppers Peter Piper picked. If Peter Piper picked a peck of pickled peppers, where's the peck of pickled peppers Peter Piper picked?
Yeah, great job, Kaivan. Aaron, would you like to try this tongue twister? So this last one.
Peter Piper picked a peck of pickled peppers. A peck of pickled peppers Peter Piper picked. If Peter Piper picked a peck of pickled peppers, where's a peck of pickled peppers Peter Piper picked?
Okay, thanks, Aaron. That is a very hard one, so good job. And Coco, would you like to try? Coco, I think your voice is a little soft. I can't really hear you. Maybe check your device settings or something. Okay. While we have that going, oh, you just finished? Maybe you might want to check your device settings for your microphone or something. Okay. Well, now let's move on to our word pronunciations. Okay, so just some really hard words that might be a little tricky to pronounce. So let's start with this first word, Oobleck. Oobleck. Okay, repeat after me. So turn on your mics. Oobleck.
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 Okay, looks like that's all. So this was Oobleck. This word is actually from a Dr. Seuss book. It's named after this creature from Dr. Seuss. So Oobleck, which is what we'll learn today, is a very strange substance. Okay, and I'll just leave that for now, and we'll learn more about it later. Okay, so Oobleck. Next word, dissolve. Dissolve. Okay,
Dissolve. Dissolve.
Dissolve.
Dissolve. Jagger, would you like to try this one? Dissolve.
Dissolve.
Great job. Aaron?
Dissolve.
Dissolve. Good job. Henry? I see you unmuted, but I couldn't really hear you. Well, hopefully you repeated that. So, dissolve. Okay? Okay, next one. That's a little longer word. Newtonian. Newtonian.
Newtonian.
Newtonian.
Yep, great job, Kaivan. Newtonian. Okay, so this is an adjective, so it describes another word. So a Newtonian fluid is something we'll see a lot in our article. Okay, and next word, fluid. Fluid.
Fluid.
Fluid, great job. And next one, frustrating. Frustrating.
Frustrating. Frustrating.
Great job. Lulu, can you try this?
Frustrating. Frustrating.
Yep, great job. I liked how you sounded that out. Frustrating. Those are 3 syllables. Jagger, can you try this?
Frustrating.
Good job. Frustrating. Okay. And next one, molecule. Molecule. Your turn.
Molecule. Molecule.
Yes, Jagger?
Molecule.
Okay. I see Kayan has pronounced it. Jagger?
A molecule.
Okay, so very close, Jagger. So this U is molecule. So you're kind of saying ooh, or like there's this Y-ish sound, so it's molecule. Okay, try again.
Molecule.
Great job. This one's better. Okay, great job. Molecule. And last one, platelets. Platelets.
Platelets.
Great job, Nancy. Nicole, can you pronounce this? Platelets. Okay, thank you, Nicole. Aaron, can you pronounce this word? This last one?
Platelets.
Okay, so there's a silent E at this over here, so it's platelets. Okay, platelets.
Platelets.
Much better. Leilu, can you try this?
Platelets. Platelets.
Great job. So platelets is like a very tiny cell in your blood. It's used it's used for blood clotting in case if you have like an injury or if you have a cut on your finger, for example. Platelets are the cells that kind of stop the bleeding. Okay, so the cut doesn't bleed anymore. So that's the function of platelets. Alrighty. So let's do this little before reading, after reading little activity. So I have a few statements here, and I'm going to ask you if you agree or disagree to this statement. Okay, so let's start with this first one. The term fluid refers to gases and solids. So no wrong answers here. I just want to know what you know previously before we read the article. So if you agree or disagree, I'm actually going to put up a poll, and I'll go through them one by one. Okay, so that's the first statement. Next one is there are fluids that can seem like both a solid and a liquid. So agree or disagree. Okay, third one, ketchup is a strange fluid because it only moves when you shake it. Agree or disagree. Fourth one, no matter how hard you push on ordinary fluids like air or water, they always act the same way. Okay, and lastly, fluids like saliva, oobleck, and peanut butter respond to force non-linearly. Okay, so if you don't really know, you can just guess like agree or disagree. Okay, so let me put up a poll and you can go ahead and answer that. So I'll give you a few seconds to do that. Okay, one person has answered. Thank you. 3 people have answered. Okay, 10 more seconds. Okay, let's end this now. Alright, so for this first one, it looks like half of you are saying true and half of you are saying agree and half of you are saying disagree. I'll skip that one for now. Second one, there are fluids that can seem like both a solid and a liquid. Okay, 3 of you say agree, so we'll put an A here. Okay. Third, ketchup is a strange fluid because it only moves when you shake it. Half of you are saying yes and no. Okay, we'll skip that for now. Number 4, no matter how hard you push on ordinary fluids like air or water, they always act the same way. 3 of you are saying agree. Okay, so we'll put an A there. And lastly, fluids like saliva, oobleck, and peanut butter respond to force non-linearly. Okay, and most of you are saying agree. Alright, and for these ones, we'll just put, I guess I can put the A. Okay, so after we read the article, we'll get back to this, and we'll see how our responses changed, okay? Alright, so let's take a look. Oobleck Can't Make Up Its Mind by India James, published in 2022. Okay, can anyone, or would anyone like to start reading over here? So, have you ever? Okay, go ahead, Nancy.
Have you ever played with slime? In this informational text, India James teacher teaches about non-newtonian fluids like slime. Try this. Mix 1 cup of cornstarch with half a cup of water. Stir and stir and stir until all the cornstarch is dissolved. You can add food coloring too if you want. Take 1 finger and push on the mixture slowly. Your finger will sink right in. As long as you keep moving the mixture slowly, you can play with it like it's mud.
Okay, thank you, Nancy, for reading. So, just a little introductory paragraph. This is like introducing what this article is about, and it asks, have you ever played with slime? Well, in this informational text, India James teaches about these non-Newtonian fluids like slime. So this really interesting substance. So this first paragraph begins with kind of like a recipe or instructions telling you how to make this this weird thing, I guess. So mix 1 cup of cornstarch with a half cup of water, and then you stir it together until all the cornstarch is dissolved. So does anyone know what the word dissolved is? Or what's the definition of this word? So what does dissolve mean? Aaron, do you know what dissolve means?
What?
So do you know what the word dissolve means?
Yes.
Yes? What is it?
It's just like solely like blend together.
Yeah, you're on the right track. It's like blended together, right? So this is stirred. So stir and stir and stir, like until everything is mixed well together. Or like another definition would be like mixed completely within a liquid, right? So, and stir until all the cornstarch is dissolved within the liquid, or in this case, it's water, okay? And then if you take 1 finger and push on the mixture slowly, your finger will sink right in, and as long as you move very slowly, you can play with it like it's mud, okay? All right, next paragraph. Kaiben, can you read this next paragraph? Over here.
Now try pushing on the mixture again, but this time push really hard and fast. It feels like you're pushing on concrete. The same mixture changed depending on how fast you pushed it. This crazy substance is called Oobleck, and it can't decide if it's a solid or a liquid.
Okay, thank you, Kyvan. Alright, so now you can see why the title is named Oobleck Can't Make Up Its Mind. Okay, so now if you try to push on the mixture again, but this time really hard and fast, it feels like you're pushing on concrete or something really solid, right? So this same mixture changed depending on how fast you pushed on it. And this substance is called Oobleck. Okay, that's the name, and it can't decide if it's a solid or a liquid. Okay, so here I have an image of Oobleck. As you can see, this person maybe pushed or kind of grabbed at it over here. So, it kind of looks like jello at the sides. It's kind of crumbly over here. But over here, on the outside, it kind of seems like a puddly pool of milk or something. Right, so this is a substance called Oobleck. So as you can see, this is like a solid, but over here around it is kind of like a liquid. Not sure if you played with this kind of substance before, but it's really interesting. Like if you really squish it, it's like Play-Doh, but if you let it flow, it's like liquid. So it's really strange. Okay, Blaylu, can you continue reading here?
Oobleck is a funny word to say, but it's an even funnier substance to play with. Usually materials are one of the three states of matter: solid, liquid, or gas. But Oobleck can seem like both a solid and a liquid and solid. How does this happen? Well, rate how fast or slowly a force is applied makes a big difference for a substance like Oobleck. That is why this is because it's what's known as a non-newtonian fluid.
Okay, thanks, Blaylu. Great reading. So over here it goes on to talk about Oobleck, and it's a funny word to say, right? Oobleck sounds really funny, but it's an even funnier substance to play with. Well, usually materials are one of three states of matter: solid, liquid, or gas, right? But Oobleck can seem like both a liquid and a solid. Well, how does this happen, you might ask? Rate which is how fast or slowly a force is applied, makes a big difference for this kind of substance. And this is what's known as a non-Newtonian fluid. It's named after Sir Isaac Newton. Okay, Jagger, would you like to continue reading here?
Newtonian fruits get their name from Sir Isaac Newton, who was a well-known mathematician and scientist. He was the first person to describe how the liquids behave using math. These are ordinary types of fluids like water and air. Scientists use the word fluid for both for both liquid and gases. No matter how you push on them, these fluids always act the same way.
Okay, thank you, Jagger. Just a minor note, this word is pronounced fluid. Okay, so we're focusing on the U here, so fluid. Okay, fluid. Okay, but great job. So Newtonian fluids get their name from Sir Isaac Newton. Okay, this person here, who was a well-known mathematician and scientist. Why? Well, for one thing, he was the first person to describe how the liquids behave using math. Okay, so that's really interesting. These are ordinary types of fluids like water and air. So, no matter how hard you push on them, they'll always act the same way, right? So, and another note is that fluid is used for both liquids and gases. So anything that flows, okay? And no matter how you push on them, these will always act the same way, okay? So this was talking about Newtonian fluids. Okay, next. Aaron, can you continue reading here, please?
Non-newtonian fluids, on the other hand, are weird. These are the types of fluids that are like Oobleck. They change depending on how they're being pushed. All non-Newtonian fluids change with rate.
Okay, thank you, Aaron. So this is like a compare contrast. So meanwhile, non-Newtonian fluids, on the other hand, are weird. These are the types of fluids like Oobleck. Okay, so this substance over here. So they change depending on how they're pushed. So all non-Newtonian fluids change with rate, how they're being pushed. Okay, but non-Newtonian fluids don't just exist in science experiments. They're more common than you might realize. Non-Newtonian fluids are actually all around us. All right, Nicole, can you continue reading over here, please? I see you're unmuted, but I can't seem to be hearing you. Nicole, I think you were reading, but I couldn't really hear you. So maybe check your device settings again or something. Okay, Nancy, can you continue? You can continue here.
Next time you squirt ketchup from a bottle, watch the last drop. If it were a bottle of water, the last drop would fall down. But the last drop of ketchup pours back into the bottle. It's almost as if the ketchup was acting a little bit like a rubber band. It pours up and into the bottle because ketchup is a non-Newtonian fluid, just like Oobleck.
Okay, thank you, Nancy. So this, what this paragraph is talking about is an example of a non-Newtonian substance, and that is ketchup. So the next time you squirt ketchup from a bottle, watch the last drop. Okay, so if it were a bottle of water, then it would just drop right down because of gravity, right? But the last drop of ketchup actually pulls back into the bottle, and it's almost as if the ketchup was acting like a rubber band, right? So if you pull on a rubber band, it's going to really stretch. So but in this case, it's kind of pulling back into the bottle, right? So it pulls up and into the bottle because ketchup is a non-Newtonian fluid, just like Oobleck. Okay, so ketchup and Oobleck are both non-Newtonian substances. Okay. Kaibin, can you continue reading here, please?
Another frustrating thing about ketchup is getting it out of the bottle. You can tip the bottle upside down, but for a long time nothing happens. Then it seems like a whole bunch of ketchup comes out at once. What's going on?
Okay, thanks, Kaibin. So this is like a little rant about getting ketchup out of a bottle. So you can tip the bottle upside down, but for a long time, nothing happens. It's not like water. It's not just going to flow out. Okay, and then it seems like a whole bunch of ketchup is coming out at once. Well, what's happening here? Okay, and these next few paragraphs kind of explain the science behind it. Okay, Henry, can you continue reading here, please? Here. Henry, are you here?
Where did I start reading?
So over here. It's all a matter.
It's all a matter of what ketchup is made of. Ketchup is made by mixing tomato paste and sugar with some other ingredients. When these are mixed together, microscopic molecules form long chains called polymers. Usually, these polymer chains are tangled together. They stay tangled until enough force is applied to stretch them out.
Okay, thanks, Henry. So this is a little explanation here. So it's all a matter of what ketchup is made of. So like the particles, right? So ketchup is made by mixing tomato paste and sugar with some other ingredients like spices and things like that. And when they are mixed together, these microscopic molecules, very long words, but just these very tiny invisible molecules, they form long chains called polymers. So if you can imagine, a polymer is like a string of beads. So the beads would represent like those molecules, and if you have a string of beads, then that's like a chain of polymers. Okay, so usually these polymer chains are tangled together. They're kind of like spaghetti. They're all tangled together, and they stay tangled until enough force is applied to stretch them out. So again, with that bowl of spaghetti, if you put enough force on it, like if you, I don't know, if you turn it upside down, well, hopefully they start to untangle, right? So that's kind of like polymers. They stay tangled together if they're like at resting state. If you apply some force on it, it'll start to untangle itself. Okay. Leilu, can you continue reading here, please?
When the bottle is upside down but no ketchup is coming out, the long chains of molecules are tangled together. When there's enough force from gravity after the bottle is upside down, the chains become unorganized. Unfortunately, all the molecule chains get organized at once. Lots of ketchup comes out at the same time.
Okay, thanks, Leilu. So this is a continued explanation. So when the bottle is upside down but no ketchup is coming out, the long chains are still tangled together. But when there's enough force from gravity after the bottle is upside down, they soon become organized. And unfortunately, they all become organized at the same time. So that's why if you hold it for a while and then it all comes down, that's because all those chains have become organized and all that ketchup comes out at the same time, which is a little frustrating sometimes, right? Okay, and last paragraph, I believe. Aaron, can you continue reading? Here.
Your body is full of non-newtonian fluids. Have you ever spit out toothpaste and found line of sticky saliva stretching down with it? Then what happened if saliva acted like water? Saliva is a non-Newtonian fluid. Blood is also a non-Newtonian fluid. Red blood cells, white blood cells, and platelets float in plasma. This combination of parts make blood act differently than a normal fluid. The liquid inside your joints that helps cushion motion is also a non-Newtonian fluid. These fluids all change how they behave depending on how they're being pushed. It's part of what makes our body work well.
Okay, thanks, Aaron. So this paragraph is talking about non-Newtonian fluids in our bodies. So your body is full of non-Newtonian fluids. So if you ever spit out toothpaste and you saw a line of sticky saliva stretching down with it, well, saliva is a non-Newtonian substance. It's not like water. It's very stretchy or sticky. It's like sticking to itself, right? So this wouldn't happen if it acted like water, and it's a non-Newtonian fluid. Another example is blood, because it has lots of cells in them, like red blood cells, white blood cells, and platelets. They all float in a substance called plasma. And this combination, this kind of mixture, is what makes blood act differently than a normal fluid, like air or water. Okay? And also, something else is the liquid inside your joints. So I searched this up. It's actually called synovial fluid. It's like what cushions your it's what cushions your joints, like when you exercise or when you move. Okay? So this fluid is also non-Newtonian. Okay? And these fluids all change how they behave depending on how they're being pushed. Okay, and that's what makes our bodies work well. Because, if you could try to imagine if our blood was like water, that'd be really strange. Like, if you jumped up and down, then you can just imagine the water in your blood vessels kind of jumping up and down inside your body too. So, yeah, good thing our blood doesn't act like water. It's a non-Newtonian fluid. Okay, and last sentence. There are lots of weird and wacky ways that fluids behave all around us. Okay, and that's the end of the article. Okay, so here I have some little comprehension questions. Okay, so let's try them. Okay, question 1. Oobleck is a type of concrete, must be touched slowly, can act like a liquid or solid, or is a special kind of Newtonian gas. Okay, so is it A, B, C, or D? What do you think? Okay, so Nancy says C. Feel free to type your answer in the chat. Okay, Aaron says C. Okay, Jagger says C. Alright, so if you think it is C, then you are correct. Oobleck can act like a liquid or solid. Okay, it's not a special kind of Newtonian gas. Oobleck is not a gas. Okay, it's a Newtonian fluid. All right, great job, guys. Let's try this next one. Non-Newtonian fluids, A, act just like water or air. B, are made up of liquids and gases. C, can only be found in a science lab. Or D, act differently based on how they are handled. Okay, A, B, C, or D. Okay, Aaron says D, Nancy says D. Jagger says D. Lulu, Kyran, Henry, what do you guys think? Okay, D. Alright, you're all correct. So non-Newtonian fluids act differently based on how they are handled. Okay, great job. Okay, next one. How is ketchup like Oobleck? Is it A, it is made of sugar and other minerals? B, it acts differently based on the force put on it? C, it only moves if you shake it? Or D, it comes in a bottle? Okay, we're saying B. Anyone else? This one might be a little more difficult, but just give it a try. Okay, so if you think it was B, then you're correct. So it acts differently based on the force put on it. So that's what a non-Newtonian fluid is. Like if you push on it really hard, then it might be a little thicker or thinner. Okay, so it's really kind of strange like that. Okay, and lastly, an example of a non-Newtonian fluid in our body is blood because it is red, joints because they move, water because it is a liquid, or D, saliva because it is stretchy. A, B, C, or D. Okay, Nancy says D. Aaron says D. Kevin says D. Alright, so if all three of you are correct, it is saliva because it is stretchy. It's not like water. It doesn't flow very quickly like water. So yeah, saliva is an example of a non-Newtonian fluid. Okay, and it's not this one because it is red. Blood is a non-Newtonian substance because of the way it flows, not because of its color. Okay, and yeah, okay, great job. Let's move on to some. Actually, instead of not, we're not into vocabulary yet. Let's try to fill this out again. So now that we've read the article, let's try to do this again. So do you agree or disagree? First statement, the term fluid refers to gases and solids. Do you agree or disagree? Just feel free to unmute, okay?
Disagree.
Okay, Nancy says disagree. Do you agree with Nancy? Hopefully. So, yeah, we disagree here. So the term fluid actually refers to gases and liquids. Okay, so those are the fluids that those are the things that flow. Okay, so we disagree here. Second statement: there are fluids that can seem like both a solid and a liquid. Okay, disagree or agree? Lulu, can you try this one?
There are fluids that can seem like both a solid and a liquid.
Okay, so agree or disagree?
Agree.
Agree. Very good. That was what the article was about. Non-Newtonian fluids. Okay, they seem like a solid and a liquid. Okay. Third statement: ketchup is a strange fluid because it only moves when you shake it. Agree or disagree? Jagger, can you answer this? So what do you think?
Is A.
Agree? So you think it only moves if you shake it?
Oh, D.
Okay, so you disagree, right? So ketchup, it can flow if you just put it upside down, right? You don't have to shake it. It just moves really slowly because all those chains need to get untangled, right? Okay, great job. Statement 4. No matter how hard you push on ordinary fluids like air or water, they always act the same way. Agree or disagree, Kairan?
Agree.
Agree. Great job. So if you push on air, it'll always act the same way. If you push on water, it'll always act the same way. Okay, so agree here. And lastly, fluids like saliva, oobleck, and peanut butter respond to force non-linearly. Agree or disagree? Aaron?
Wait, what does non-linearly mean?
So non-linearly means like not at the same rate. So if you push on oobleck, it's not going to go twice as fast. Or yeah, if you push it just one times hard, it's just going to flow 1 times as fast. If you push on it 5 times as fast, then it's gonna flow 5 times the rate. Okay,
Disagree.
Wait, okay, I might have not explained it a bit wrong. So non-linearly is like linear means in a straight line. So if you push on water, it's going to flow linearly. But if you push on a non-Newtonian substance, it's actually not going to flow linearly. Okay, so let's go back to this article. I think it said something like so over here it says they change depending on how they're being pushed. But for ordinary fluids like water and air, no matter how you push on them, they always act the same way. So that would be like linearly, okay? But for non-Newtonian fluids, they change how they flow depending on how they're being pushed. Okay, so for this statement, fluids like saliva, oobleck, and peanut butter respond to force non-linearly, so they don't respond to the force. So they respond to the force differently. Okay, so this would be agree. Okay. Do you understand now, Aaron? Hopefully.
Yeah.
Okay. Yeah. Okay. All right. Let's move on. Okay. Vocabulary. Would anyone like to read this definition and example sentence? Okay, Nancy, go ahead.
Dissolve, to mix completely with a liquid. For example, sugar is a soluble substance, which means that it dissolves in water.
Okay, so sugar is a soluble substance, so it dissolves in water. It mixes completely with water if you mix the sugar in it. So dissolve means to mix completely with a liquid. Okay, thanks, Nancy. Next one, oobleck. Jagger, can you read this out loud, please?
A mixture of cross stretch and water that behaves like a liquid at rest and like a solid when pressed is applied.
Okay, thanks, Jagger. So this is a mixture of cornstarch and water that behaves like a liquid at rest and like a solid when pressure is applied. Okay, so if you punch it, it's going to feel very hard, like concrete. Okay. Next word, substance. Aaron, can you read this?
Substance, a material of a particular kind.
Okay. And this example sentence.
The floor was covered with a white powdery substance, which turned out to be flour.
Okay, thanks, Aaron. So a substance is a kind of material or a particular kind of material. So, for example, the floor was covered with a white powdery substance. Okay, it was covered with a white powdery material, which turned out to be flour. Okay, and how about this one? Lilu, can you read this definition out loud, please?
Polymer, a long molecule made from many smaller and simpler molecules.
Okay, and this example sentence?
In terms of construction, the Pathfinder's internal structure is made of polymer tubing reinforced with carbon fiber.
Okay, thank you, Lulu. So this one's a little more scientific. Let me just explain this. So a polymer is a long molecule made from many smaller and simpler molecules. So here's a little illustration of like a polymers. So again, take that bead example. So if you had one bead, that'd be like one simple molecule. Take 2 beads and 3 beads and 4 beads. Okay, so you string them together, that would make a polymer chain. So it's all of these simple molecules put together that makes a longer molecule. Okay, so in this example sentence, in terms of construction, this kind of structure is made of polymer tubing. It's made of lots of simpler molecules put together. So polymer tubing reinforced with this material called carbon fiber. Okay, so that's polymer. Okay, and next word, microscopic. Henry, can you read this out loud? Henry, are you here? Okay, Coco, can you read this definition out loud, please?
Microscopic, invisible without the use of microscope, very small.
Thanks. And this example sentence? Coco?
There's a microscopic crack in the diamond.
Okay, thanks. So microscopic means very small. It's or invisible without the use of a microscope. So the example sentence, there's a microscopic crack in the diamond. So a very small, invisible crack in the diamond. Okay. And last word, molecule. Kyron, can you read this out loud, please?
Molecule, the smallest unit or part of something. The specialists study the DNA molecule to see if the child was related to the nurse.
Okay, thank you, Kyron. So molecule is the smallest unit or part of something. So in science or chemistry, the molecule is like the smallest unit. So it would be an atom, right? So molecule. In the example sentence, the specialist studied the DNA molecule, a small part, to see if the child was related to the man. Okay, so like this is a DNA test to see if this child is related to this man. All right, so those are vocabulary words, and yeah. Okay, so let's test your knowledge of this vocabulary. So what is the word for the definition, a mixture of cornstarch and water? Okay, so what word would this be?
Black.
Okay, so Nancy says Oobleck, and you're correct. So Oobleck is a mixture of cornstarch and water. Good job. How about this one? To mix completely with a liquid. What would this word be? Jagger, what do you think? No? Okay, Kyren, you can try this.
Dissolve.
Good job. So dissolve means to mix completely with a liquid. Alright. Third one, a particular kind of material. So what is a particular kind of material?
Substance.
Substance. Yes. Good job, Nancy. Substance is a particular kind of material. How about this one? The smallest unit or part of something. Lulu, what do you think? So what is the smallest unit or part of something? What is the word for this?
Molecule.
Good job, molecule. A molecule is the smallest unit or part of something. Okay. Next one. What about invisible without the use of a microscope? Okay, which word is that? Coco?
Wait, what?
So, what's the word for this definition? So invisible without the use of a microscope.
Microscopic.
Yes, great job. It has the word microscope in it. So microscopic, it's really tiny or very invisible. Okay, great job, Coco. And last one, a chemical substance consisting of large molecules made from many smaller and simpler molecules. Aaron, what do you think? So what's the word for this last definition? I know this one's a little hard.
Polymer.
Great job, polymer. So remember that string of beads, right? So polymer is a chemical substance consisting of these small, simpler molecules. All right, great job. Okay, so here I kind of made a sketch note of all the things in the article that the article mentioned. I've also put this on the FutureEd website, so if you'd like to take a look, you can go ahead and do that after class. Okay, so it's like a little note for you to look back. So starting here, Oobleck, a non-Newtonian fluid. So Sir Isaac Newton was the first person to describe how liquids behave using math, and that's why they're called Newtonian fluids. Okay, and what is a fluid? Well, it's anything or any gas or liquid that flows. Meanwhile, non-Newtonian fluids are really strange, and they act differently based on the force, time, and or speed on how they are handled. So how fast you push on them or how slow. Okay, so some examples would be like toothpaste, ketchup, slime, peanut butter, okay, those types of fluids. And this is a little vocabulary bank that we just went over. Okay, and we have about 8 minutes left of class, so let's take a look at this video before we end. Alright, so this is about ketchup in particular, how it acts like a non-Newtonian fluid. Okay, so let's take a look.
French fries are delicious. French fries with ketchup are a little slice of heaven. The problem is, it's basically impossible to pour exactly the right amount. We're so used to pouring ketchup that we don't realize how weird its behavior is. Imagine a ketchup bottle filled with a straight-up solid like steel. No amount of shaking would ever get the steel out. Now imagine that same bottle full of a liquid like water. That would pour like a dream. Ketchup, though, can't seem to make up its mind. Is it a solid or a liquid? The answer is, it depends. The world's most common fluids, like water, oils, and alcohols, respond to force linearly. If you push on them twice as hard, they move twice as fast. Sir Isaac Newton of Apple fame first proposed this relationship, and so those fluids are called Newtonian fluids. Ketchup, though, is part of a merry band of linear rule breakers called non-Newtonian fluids. Mayonnaise, toothpaste, blood, paint, peanut butter, and lots of other fluids respond to force non-linearly. That is, their apparent thickness changes depending on how hard you push, or how long, or how fast. And ketchup is actually non-Newtonian in two different ways. Way number one. The harder you push, the thinner ketchup seems to get. Below a certain pushing force, ketchup basically behaves like a solid. But once you pass that breaking point, it switches gears and becomes 1,000 times thinner than it was before. Sound familiar, right? Way number two. If you push with a force below the threshold force, eventually the ketchup will start to flow. In this case, time, not force, is the key to releasing ketchup from its glassy prison. All right, so why does ketchup act all weird? Well, it's made from tomatoes. Pulverized, smashed, thrashed, utterly destroyed tomatoes. See these tiny particles? This is what remains of tomato cells after they go through the ketchup treatment. And the liquid around those particles, that's mostly water and some vinegar, sugar, and spices. When ketchup is just sitting around, the tomato particles are evenly and randomly distributed. Now let's say you apply a weak force very quickly. The particles bump into each other, but can't get out of each other's way, so the ketchup doesn't flow. Now let's say you apply a strong force very quickly. That extra force is enough to squish the tomato particles, so maybe instead of little spheres, they get smushed into little ellipses. And boom, now you have enough space for one group of particles to get past others, and the ketchup flows. Now let's say you apply a very weak force, but for a very long time. Turns out, we're not exactly sure what happens in this scenario. One possibility is that the tomato particles near the walls of the container slowly get bumped towards the middle, leaving the soup they were dissolved in, which remember is basically water, near the edges. That water serves as a lubricant between the glass bottle and the center plug of ketchup, and so the ketchup flows. Another possibility is that the particles slowly rearrange themselves into lots of small groups, which then flow past each other. Scientists who study fluid flows are still actively researching how ketchup and its merry friends work. Ketchup basically gets thinner the harder you push, but other substances like Oobleck or some natural peanut butters actually get thicker the harder you push. Others can climb up rotating rods or continue to pour themselves out of a beaker once you get them started. From a physics perspective, though, ketchup is one of the more complicated mixtures out there. And as if that weren't enough, the balance of ingredients and the presence of natural thickeners like xanthan gum, which is also found in many fruit drinks and milkshakes, can mean that two different ketchups behave completely differently. But most will show two telltale properties: sudden thinning at a threshold force, and more gradual thinning after a small force is applied for a long time. And that means you could get ketchup out of the bottle in two ways. Either give it a series of long, slow, languid shakes, making sure you don't ever stop applying force, or you could hit the bottle once, very, very hard. What the real pros do is keep the lid on, give the bottle a few short, sharp shakes to wake up all those tomato particles, and then take the lid off, and do a nice controlled pour onto their heavenly fries.
Okay, and there is the video. Hopefully now you understand more about Newtonian and non-Newtonian fluids. Okay, so remember this was talking about ketchup and why it's so hard to get it out. Right, so ketchup actually, just a little summary. So ketchup acts like a non-Newtonian fluid in two ways, right? So way number one is the harder you push, the thinner ketchup gets. So if you push really hard, it's going to get really thin very quickly. But the second way is if you kind of leave it upside down. If you push with a force like that's below the threshold force, so really weakly for a long time, it'll eventually flow out. So it's basically time, not force, that gets the ketchup out. Okay, so those are just two really interesting ways how ketchup flows, and also compared to some other non-Newtonian fluids like Oobleck, which was mentioned in the article. So Oobleck actually gets thicker the harder you push, but ketchup gets thinner the harder you push. So those are some differences. Something else that's really interesting is you can some can actually climb up rotating rods, and some can pour themselves out of a beaker continuously if you get them started. So yeah, I think non-Newtonian fluids are really interesting. And yeah, does anyone have any comments or questions? If not, that is all for today. Thank you for joining me, and I hope you have a fantastic day. Okay, I'll see you next time. Bye.
Bye.